back to my channel. So today we will discuss about Ampere's circuital law, which is another important topic for the board exam. It is used to find the magnetic field just like biot-savart's law. If the geometries are having some symmetry, the Ampere's circuital law makes the problem easy. So here we will go with Ampere's circuital law. In electrostatics, Gauss' law is an alternative form of Coulomb's law. Similarly, in magnetostatics, Ampere's circuital law is an alternative form of biot-savart's law, where the link of the biot-savart's law is provided in the description box. Both are used to find the magnetic field. Ampere's circuital law gives a relationship between magnetic field and the current passing through that circuit, or the current which produces that magnetic field. So we can state Ampere's circuital law as it is a line integral of the magnetic field around a closed circuit is equal to mu0 times the current passing through that circuit. Or mathematically we can represent, or we can write Ampere's circuital law as integral b dot dl is equal to mu0 into I. Line integral of magnetic field through that circuit is equal to mu0 times the current passing through that circuit, where mu0 is permeability. In simplified form, Ampere's circuital law can be stated as if the magnetic field is directed along the tangent at every point of a closed loop whose perimeter is L and its magnitude remains same or remains constant along the curve, then BL is equal to mu0 I, where B is the magnetic field, L is the perimeter, mu0 is the permeability, and I is the current through that closed loop. And this closed loop is known as Amperian loop. It is a geometrical entity and it is not a real wire loop. Proof for Ampere's circuital law. So here we will prove Ampere's circuital law for a straight current carrying conductor. According to biot-savart's law, the magnetic field at a point P from r distance from a straight current carrying conductor B is equal to mu0 I divided by 2 pi r, where r is the distance between point P and the straight current carrying conductor. And this was the first application of biot-savart's law, which is given in the description box. Now here the magnetic field is along the circumference of this circle. So in order to find the line integral of magnetic field, we are considering a small current element dl, and here dl and the magnetic field both are tangential to the circle or tangential to the circumference of the circle. So since they are tangential, since both are tangentials, the angle between magnetic field and dl is 0. So integral b dot dl is integral b dl cos theta. Since theta is 0, we can write it as integral b dl. So this magnetic field B is equal to mu0 I by 2 pi r. I am going to integrate with respect to dl. So integrating both sides with respect to dl, the equation becomes integral closed integral b dl is equal to integral of mu0 I divided by 2 pi r into dl. Here mu0 I by 2 pi r in the right side is a constant. We can take it outside of the integral. So the equation becomes mu0 I by 2 pi r integral dl. Here the magnetic field is along the circle. So integral dl is the circumference of the circle. So instead of integral dl, we can write the circumference. Well, circumference of a circle is 2 pi r, where r is the radius of the circle. So this equation becomes mu0 I divided by 2 pi r into 2 pi r, where 2 pi r cancels. So the final equation is integral b dot dl is mu0 I. This is the proof for Ampere's circuital law. According to Ampere's circuital law, integral b dot dl is equal to mu0 I. So this law is applicable for any assembly of the current or any arbitrary closed loops. Application of Ampere's circuital law to a straight conductor. So here we will consider a straight conductor which is carrying a current I. In order to apply Ampere's circuital law, first of all we will consider an Amperian loop. Here the Amperian loop is in circular shape where the magnetic field is along this Amperian loop or along the circular path. So if I am consider a small elementary length dl, both dl and the magnetic field will be tangential to the circle. So integral b dot dl can be written as integral b dl because angle between b and dl is 0. So b dl cos theta becomes b dl, or b into this is equal to b into integral dl, or b into integral of dl is the circumference of the Amperian loop. So it is 2 pi r. So integral b dot dl is equal to b into 2 pi r. According to Ampere's circuital law, now we will apply Ampere's circuital law. Integral b dot dl is equal to mu 0 I. Instead of integral b dot dl, I can write it as b into 2 pi r. So b into 2 pi r is equal to mu 0 I, or b is equal to mu 0 I divided by 2 pi r. Thus, we find the magnitude of magnetic field at a distance r from a straight current carrying conductor using Ampere's circuital law, that is b is equal to mu 0 I divided by 2 pi r, where r is the radian of the Amperian loop. Magnetic field inside a solenoid using Ampere's circuital law. In a solenoid, every point inside the magnetic field will be uniform and 0 outside the solenoid. So here this is a cross-sectional view of a solenoid where the direction of magnetic field or magnetic field comes out of the plane of the paper at the points marked dot, so the top of the solenoid, and below the points are marked as cross where the direction of magnetic field is into the plane, enters into the plane. So in order to apply Ampere's circuital law, here we have to consider an Amperian loop. A, B, C, D is a rectangular Amperian loop of length L. So we are going to apply Ampere's circuital law. According to Ampere's circuital law, integral closed integral b dot dl is equal to mu 0 I. Since here the Amperian loop is a rectangular loop, we have to consider all the four lengths, that is A to B, B to C, C to D and D to A. So I can write integral b dot dl as integral over A to B, b dot dl plus integral b to C, b to C, b dot dl plus next C to D. So integral C to D b dot dl plus, and the last length is D to A. So it is integral D to A b dot dl. Okay, here if I am considering BC and AD, BC and AD are perpendicular to the magnetic field. BC and AD are perpendicular to the magnetic field. So here theta is equal to 90 degree. Since theta is 90 degree, integral b dot dl becomes 0. Here integral b to C b dot dl is equal to integral d to A b dot dl is equal to integral b dl cos 90, where cos 90 is 0. So here this becomes 0. So these two terms, b to C is equal to 0, d to A is equal to 0. Similarly, if I am considering the length C to D outside the solenoid, the magnetic field outside the solenoid is 0. So this term C to D also becomes 0. So integral C to D B dot dl is 0 because CD is the length of the ampere loop which lies outside the solenoid. Outside the solenoid, the magnetic field is 0. So the only existing term is integral A to B dl which lies parallel to the magnetic field inside the solenoid. So here I am writing integral A to B dot dl which is equal to integral A to B dl cos 0 because B and dl are parallel to each other. Cos 0 is 1. So the equation becomes integral B dl, or I can write this as BL. B into integral dl, integral of the loop, length of the loop or length of AB is L. So integral dl can be replaced as BL. So integral B dot dl is equal to BL. Okay, equal to mu 0 I. Suppose n is the number of turns per unit length. Therefore, total number of turns n will be equal to n into L. If n is the number of turns per unit length, then total number of turns is equal to NL. So I can write this equation as BL is equal to mu 0 NL into I, multiplying the total number of turns with mu 0 I. L cancels, and here is the equation for magnetic field inside a solenoid. B is equal to mu 0 Ni, where N is the total number of turns per unit length. So thus you derive the magnetic field inside the solenoid using Ampere's circuital law. B is equal to mu 0 Ni, where N is the total number of turns per unit length. A copper wire wounded closely over a helix is known as a solenoid. So in the case of a solenoid, there will be n number of turns or n number of circular loop. And we already know that each circular loop or current carrying circular loop will be having a magnetic moment, and that magnetic moment M is equal to Ia, where I is the current and A is the area of the loop. So each turn has a magnetic loop. And each turn is arranged in such a way that the magnetic or the poles of one turn is close to the unlike pole of other turn. For example, if a current carrying circular loop have a magnetic moment, or the current carrying circular loop has north pole as well as the south pole. Solenoid is arranged in such a way that the adjacent poles cancels each other. For example, if this is the first loop, consider this as a solenoid. If this is the north pole, the adjacent loop will be having the south pole, and polarity of this circular loop can be determined using clock rule, which we already discussed in biot-savart's law. So you can check it out for the description box. So in such a way, the n number of turns or n number of circular loops are arranged to form a solenoid. So in between the solenoid, there will be no poles because they cancels each other. But at the end, definitely there will be the poles. So solenoid has a polarity, and this polarity can be determined using Ampere's right hand rule as well as clock rule. Now what is Ampere's right hand rule? If we have a solenoid, current carrying solenoid, hold the solenoid in the right hand in such a way that the fingers, curved fingers are pointing in the direction of the current, then extended thumb gives the direction or gives the north pole. The extended thumb will be towards the north pole of the solenoid. So by using Ampere's right hand rule, we can determine the polarity of the solenoid. Solenoid is equivalent to a bar magnet. It has a north pole as well as a south pole. Hold the solenoid in the right hand in such a way that the curved fingers gives the direction of the current, then extended thumb gives the direction of, or extended thumb will be towards the north pole of the solenoid. Magnetic field due to a toroidal solenoid. If a solenoid is bent to form a ring, that is known as a toroid. So toroid is nothing but copper wires are closely wounded around to form a ring. So this is a toroid. So we will find the magnetic field due to the toroid at a point inside the toroid, let it be P. At a point on the toroid, let it be Q. And at a point outside the toroid, let it be S. Okay. So first of all, we will consider the point inside the toroid. That is point P. Applying Ampere's circuital law, integral B dot dl is equal to mu 0 I. Inside the toroid, that is an open space or open cavity in the toroid, current I is equal to 0. No current is passing through this open space. So current I is equal to 0. So integral B dot dl is equal to 0 or B is equal to 0. So magnetic field inside the toroid in the open cavity of the toroid is 0. Now we will consider on the toroid, that is Q. Here Q is a point on the toroid. So in order to apply Ampere's circuital law, here we are considering an Amperian loop which is in circular shape. Let radius of that Amperian loop be R. According to Ampere's circuital law, integral B dot dl is equal to mu 0 I. Here integral B dot dl is equal to integral B dl, because here angle between B and dl, both the magnetic field as well as the current element dl are tangential to the circle. Amperian loop is a circle. Both magnetic field and dl are tangential to the circle. As a result, angle between them is 0 degree. So integral B dot dl can be written as B dl, or this is B integral dl, where integral dl is the circumference of the circle. So I can write it as B into 2 pi r. So let this be the equation number 2. Equating 1 and 2, we can write B into 2 pi r is equal to mu 0 I, or B is equal to mu 0 I divided by 2 pi r. So this is the equation for magnetic field for one term, that is B is equal to mu 0 I divided by 2 pi r. So if there are n number of turns per unit length, so if n is the number of turns per unit length, then total number of turns n is equal to n into 2 pi r. If n is the number of turns per unit length, then total number of turns can be written as n into 2 pi r. So here I am multiplying the total number of turns. So B is equal to mu 0 n into 2 pi r I divided by 2 pi r. 2 pi r cancels, and the final answer is B is equal to mu 0 ni. Same equation as that of the solenoid, mu 0 ni, where n is the total number of turns. So that's all for today. We discussed Ampere's circuital law and its application, which is one of the important topic for the board exam. For sure you can expect a question from Ampere's circuital law. So we will see with yet another interesting topic from magnetism. So if you find this video helpful, please don't forget to subscribe, give me a thumbs up and also share with your friends. Thank you.